let us start our afternoon session. I'm very glad to introduce the first speaker, is Mahender Singh. Please.
Am I audible?
Yes, yes.
Okay. Thank you very much for the introduction. So let me first thank the organizers for giving me opportunity to speak in this conference. I wish I could come to Sochi. I have never been to that part of Russia. So maybe sometime later. Okay, so today I'm going to talk about finiteness of canonical quotients of Dehn quandles of surfaces. So I will explain the terms as they come in the slide. So canonical quotient here, I mean, I will explain those. So these are some kind of torsion analog, as you can think in case of groups. So you'll see. Okay. All right. So I'm having difficulty in moving. Okay. All right. So let me begin with the definition of quandle. So quandles are algebraic systems with a single binary operation, okay, and with some axioms, which are basically algebraic formulation of the three right-dimensional moves of planar diagrams of knots and links, which are embedded in the three space, okay. So more precisely, you have a set, non-empty set with a binary operation, which satisfy the property idempotency x star x is x, and given x and y, there is a unique element z, so that x star z is z star y is x, okay, and you have right distributivity. So x star y star z is same as x star z star y star z. So let us see immediate connection with the knot theory. So suppose you have a knot in the three space and you take a regular projection of that and you orient your knot diagram. And I said the rule as follows. So whenever you have an over arc for a positive crossing, so over arc act on the incoming under arc x and the output is labeled by that action x star y. And similarly for the negative crossing, I just write as x star inverse y. So with this convention, it's not very difficult to check that the three right-dimensional moves, namely the first move here, okay, the second move and the third move, and if you do this labeling and chase this labeling from one end to the other, then it simply tells you, gives you the three axioms. So for instance, in case of R1, the way I have defined labeling tells you that x star x should actually be x, because I want it to be same as the right hand this untwisted segment. Similarly, in the second one, R2, what I get is x star y star inverse y should be same as the arc x, okay? And this is same as axiom 2, because remember axiom 2 said that given x and y, there is a z, so that z star y is x. So that means the right multiplication by each element is a bijection. And this diagram change for the third move also tells you that x star y star z is same as x star z star y star z. Okay, so these axioms are just tailor-made for knot theory. But it turns out that they appear abundantly, they are abundant in a variety of contexts throughout mathematics. And we'll talk about one aspect in this talk. So as you can expect, given an oriented knot diagram or a link diagram, you can associate a quandle with that. So how do you do that? You look at the quandle which is generated by arcs and go model the relations corresponding to the crossings. So of course, one need to check that this is an invariant and it doesn't depend on the diagram. It requires some work, but it's a well-known result and is attributed due to Sergei Matveev and David Joyce, who proved this result at the same time, 1982. So what they actually showed is that if K prime and K are two oriented knots, then K prime is equivalent to either K or the reverse of the mirror image if and only if the knot quandles are isomorphic. So it's a very strong invariant. Okay, in fact, it's stronger than the knot group in some sense. And I mean, as a toy example, if you take a trivial n-component link, then just following the rule tells you that there are no relations. So it's actually the free quandle on the number of generator, which is same as the number of components. So the link quandle of the trivial n-component link is precisely the free quandle of rank L. So besides knots and links, groups are rich sources of quandles. So I will define a class of quandle, which is what I will focus on later in this talk. So given a group G and a non-empty subset A of the group G, let us set AG to be the set of all conjugates of elements of A and G. Okay, so you take the conjugacy classes of elements of A, and this set you can equip with the quandle operation, namely conjugation, very natural operation. So you define X star Y to be Y X Y inverse. Okay, it's a quandle. And it turns out that many well-known constructions of quandles can be recovered like this. So here I would like to comment, there is a work of Valery Bardakov and Timur Nasipolo on similar construction, which is a little different in the sense that they take this external, instead of taking this conjugacy classes, they take this Cartesian product and then define some binary operation on that. And when elements of A do not represent different conjugacy classes, then that construction agrees with this. And actually for, so therefore there is some connection with that construction. And if you take A to be G itself, then you get the set of all conjugates of elements of the group G, which is just the conjugation quandle of the group. And if Fs is a free group and S is generated by a set S, then the Dehn quandle of S with respect to, of the free group with respect to the generating set, free generating set S is actually the free quandle. And there is a very recent result of Bergman, who showed that actually core quandle of any group you can realize like this. Okay, so there are many other quandles which can be realized in this form. And in fact, for example, the knot quandles of prime knots can also be realized like this. So which will follow from an observation in the next slides. So there is a way to go from, so we saw a way to go from groups to quandles. So there is a way to go from quandles to groups also. And what we do is, given a quandle, we associate a group. So which is basically the group generated by elements of the quandle, and each star relation is replaced by conjugation. So the generator corresponding to a product of two quandle element is just conjugation of one by the other. Okay. For instance, if a quandle is a trivial quandle, so then one can easily see that X star Y is just X. So this is just a commuting relation. So all the generators commute, and therefore it's a free quandle of rank N. And in fact, if we take the link quandle, then the corresponding enveloping group is precisely the link group. So in fact, these associating conjugation quandle to a group and enveloping group to a quandle, they are adjoint functors from category of groups to category of quandles. And there is a very natural map from the enveloping group of a Dehn quandle to group to the underlying group, namely just send the basis generating set EX to X. Okay, and one can check that it's actually a group homomorphism. This is the identity easy to see. And because we started with a generating set for S, it's a surjective map, and in fact one can see that this is actually a central extension of groups. So this is the point I was telling in a few minutes back, that these quandles are precisely the ones which embed into the their enveloping groups. So there is a natural map from a quandle to its enveloping group, namely which sends the quandle element to the corresponding generator of the group. Okay, and it has this following universal property, that whenever we are given a group homomorphism, a quandle homomorphism from your given quandle into conjugation quandle of a group, then this has to factor through the enveloping group. That means you can extend this map F to a group homomorphism from enveloping group to into G, such that the map eta followed by this F hat is your original map. And this property one can use and one can give a characterization of what I call Dehn quandles. So the following statements are equivalent that a quandle embeds inside conjugation quandle of a group if and only if the natural map is injective, if and only if that quandle is precisely a set of conjugacy classes of some element in some group. So therefore, the knot quandles of prime knots also satisfy this property because there is a very nice result. I'm forgetting the author, which gives a characterization of prime knots. A knot is prime if and only if knot quandle embed inside the enveloping group. So let us come to the main content of the talk. So I want to talk about quandle structures on surfaces. And we will see that this is nothing but Dehn quandle of some group that is associated to a surface, namely the mapping class group. So let me begin with the terminology. So let SGP be an orientable surface of genus G, okay, with P mark points. So we have a surface and we just mark some points, distinguished points. Then the mapping class group, which we denote by MGP of the surface, is defined as the set of isotopy classes of orientation preserving self-homeomorphisms, which permute this set of mark points or punctures. Okay, so different authors use different convention here. Some people call it mark points, some people call it punctures, depending on the context. So I will not get into details of that. So these groups have very nice generators, which are given by simple closed curves and arcs. So let me explain that idea. So a simple closed curve on a surface is an embedding of a circle into the interior of the surface. So that means it should not be touching any of these mark points or the boundary if it has a boundary. And we say that such a curve is essential if it is not homotopic to a point or to one of the punctures. A simple closed arc is an embedding of a closed interval, okay, into the surface, such that the pullback of the distinguished points is either of the the endpoints of the interval. Okay, and it is essential if the endpoints are distinct. So by abuse of notation, so we will denote the same isotopy class of a simple closed curve and isotopy class of a simple closed arc by the same notation, although they will be isotopy classes, but it doesn't really matter. Okay. So let me explain you two very important operations on the surface. So given a simple closed curve alpha and a simple closed arc B on the surface, we denote the right hand Dehn twist along alpha by T alpha and the anti-clockwise half twist along the arc B by HB. So what do I mean by that? So so look at the first picture. So you have this alpha, which is the meridian and longitude, and take this beta meridian. And if I want to consider Dehn twist along beta, so that simply means that when I approach this alpha near beta, then I trace along the direction of beta. So I'm saying right hand, so I move along the right side. And when I reach back again in the neighborhood of the same turning point, then I move along the same path. So as you can see in the second picture, so the output alpha star beta is the effect of the right hand Dehn twist of alpha along beta. Similarly, I can talk about the half twist. Okay, so this picture explains it. So this, yeah, so the red arcs and this the vertical horizontal have been taken half twist, so HBA. And this action is actually defined in this neighborhood of this arc, and on the remaining part of the surface it is identity. So it gives you a orientation preserving homeomorphism of the surface, isotopy classes of which are the elements of our mapping class group. And it turns out that they are actually generators. It is a well-known result from this theory. So coming to quandles, so let us take a very special subset of these orientation preserving homeomorphisms. So let DGP denote the set of isotopic classes of all simple closed curves and simple closed arcs on your surface. And we say it is non-separating if the complement is connected and is separating otherwise, and similarly for the arc. And in DGP, NS denote a subset of this DGP where these curves and arcs are non-separating. That means if I cut my surface along these curves and arcs, I do not make my surface disconnected. Okay. Excuse me. So such curves and arcs are called non-separating. And in the preceding slide, I explained, given a simple closed curve and a simple closed arc, I define a homeomorphism of the surface. So those I denote by Ty and Hy. I think we already defined this notation here. So now I have a set DGP and I can define a binary operation on this using these objects. So I define X star Y to be Tyx if Y is the isotopy class of a simple closed curve, and Hyx if Y is the isotopy class of a simple closed arc. So X and Y are isotopy classes of simple closed curves, for instance. Now you take the Dehn twist of X along Y, you again get a simple closed curve. Okay. And take this isotopy class, and all these operations are well defined up to isotopy, and that follows from theory of mapping class groups. So it turns out that the set DGP has this quandle structure with respect to this binary operation. Now the question is how is it related to the definition of Dehn quandle that I gave in the beginning? So here is the key. So the set of all Dehn twists along non-separating simple closed curves form a single conjugacy class in this MGP. So if we have a surface, take all non-separating simple closed curve, take Dehn twist along all of them, and it turns out that all these homeomorphisms, they form a single conjugacy class in this group MGP. Similarly, the set of all half twists along the simple closed arc, they form another conjugacy class. Okay, so if for instance, my surface doesn't have any punctures or mark points, I can just focus on simple closed curves. And all of these Dehn twists along such curves, they form a single conjugacy class. So let S be the generating set for MGP consisting of simple closed curves and simple closed arc. And it is well known that I just need only finitely many of such curves and arc to generate this group. So this is a well-known result from the theory of mapping class groups. So actually, finiteness is not really needed here, but it's a fact that we need only finitely many. As far as Dehn twists are concerned, of course, mapping class group can be generated by very few number of generators. In fact, as low as maybe 3 or something. Okay. So there is an injective map from this DGP, which is a set of all isotopy classes of simple closed curves and simple closed arcs to my mapping class group. And what is that map? The map simply take a simple closed curve to the corresponding Dehn twist and simple closed arc to the corresponding half twist and their isotopy classes. So it's an isotopy invariant. Okay. So it's a well-defined map. It's an injective map. And furthermore, this map actually satisfies this proper identity. That is tau of X star Y, which by definition was AY of X, where A could be half twist or Dehn twist. But tau is actually again half twist of this object. So it is A of Y. And one can see that this is actually just conjugation. Okay, and furthermore, this is injective. This is also, it can be easily proved that if two curves, simple closed curves, are isotopic, if and only if the Dehn twists are isotopic as homeomorphisms. So this is a well-defined map. This is in fact injective, and this is in fact a quandle homomorphism from this DGP into MGP equipped with conjugation. And what is the image? Image is precisely the set of all conjugates of this generating set S in MGP. Therefore, this DGP, which is just the set of isotopy classes of some curves, simple closed curves and simple closed arcs, can be viewed as a certain subset of conjugacy classes of elements in the mapping class group. In that sense, it's a Dehn quandle as per our definition. And in fact, this object has appeared earlier in a lot of work. So let me give a brief historical account. So the construction of Dehn quandle of a surface HGP for when there are no punctures, it appeared first in the PhD thesis of Zoe Zablo from Stony Brook. And then I think at the same time, Saichi Kamada and Matsumoto and Yetter also considered quandle structure on the set of isotopy class of simple closed arcs. They did not consider curves and arcs together. So I think so what they call these are called quandle of chords, because actually they are taking just chords joining to endpoint and taking half days around them. For instance, if my surface is a disk and if I have n punctures, then this quandle of chords is precisely the Dehn quandle of the braid group. So in general, the quandle of chords is a subquandle of DGP, which is obvious by definition. And in case of a disk with n plus 1 puncture, this can be identified with Dehn quandle of the braid group, as I mentioned. And this idea was explored by Zobler in a series of papers after his thesis, and where he connected knot links with colorings of Dehn quandles of surfaces. So there is a very curious result in this direction. That was actually our motivation for this study. But before that, let me give you one more definition. So notice that link quandles are always infinite, except for the unknot and the half link. It's a very easy exercise. And therefore, studying their finiteness properties become interesting. I mean, because they are infinite, so what kind of finiteness property they can have? So I have not mentioned here, but we have proved with Valery Bardakov and my student that these all link quandles are actually residually finite. So here we want to consider another problem. So we want to see whether their n-quandles are finite or not. Okay. Of course, their residual finiteness still remains open. We have no progress on that. So what is n-quandle of a quandle? So given a quandle, you impose additional relation that the n-fold iterated right product by any element is x. So x star y, so on is x. So in terms of right multiplication viewed as a symmetry, each right multiplication has order dividing n. Okay, so I impose this condition on my quandle, and the quotient quandle that I get, I called it the n-quandle of my group. So it was a conjecture of Joseph Pititsky in 2013 that the n-quandle of an oriented link L is finite if and only if the fundamental group of the n-fold cyclic branch cover of the three sphere branched over L is finite. So finiteness of this n quotients of link quandles is related to finiteness of the fundamental group of some three manifold one can construct over the three sphere in which your link is embedded. And this conjecture was proved recently by Hoste and Shanahan. The idea was very interesting. What they did is they extended idea of David Joyce in who introduced this term quandle. So what David Joyce showed is the link quandle can be viewed as certain poset quandle of fundamental group of the link complement divided by peripheral subgroup and some interesting quandle structure. And what these people did is they extended that idea to n quandles also. And then they used some result of Dunbar's based on Thurston's work, classification of certain orbifold to give a complete list of knots and links whose n quandles are finite for some n. So if one look at this paper, there is a table which gives a complete list of all the knots and links for which their n quandles are finite for some n. So therefore, this question whether they are residually finite still remains open, and I don't know. I really have no idea how to proceed with that. But what we consider is a little different problem, which was motivated by this curious result of Nebryzovsky and Pititsky. They showed that the knot quandle of the trefoil is actually isomorphic to the Dehn quandle of the torus. Very interesting connection. And we were thinking that maybe it happens for a lot of knots and a lot of surfaces, and unfortunately, it doesn't really happen. So we started exploring finiteness of n-quandles of Dehn quandles of surfaces. So I will take just 2 more minutes, and then I will state my result. So considering general n-quandles of arbitrary groups, we can observe the following. If G is a group generated by a set S, and let us say Gn to be the quotient of G by the normal closure of the nth powers of the generating set. Okay. Then one can make this observation that the n quotient of the Dehn quandle is finite, then the group Gn is finite. So therefore, if we know that Gn is infinite, then we know the n quotient of the Dehn quandle has to be infinite. So this we use later on to say about surfaces. And since I don't have time, I will just quickly just state this without getting into these definitions. So we want to say when the n-quandle of Dehn quandle of a surface is finite for as you vary the genus of this surface. So what really happens is that if you take the 2-quandle of the Dehn quandle of a surface, it's always finite. In fact, we give a precise description structure of this quandle, and this is this theorem that the 2-quandle of n-quandle of 2-quandle of Dehn quandle of a surface one can identify with this projective homological quandle, which also appeared in the work of Yetter. This is actually a certain subset of the homology group, and we could with the quandle operation that come from the intersection form. And for genus 2, the 3-quandle also we can identify like this, and therefore is finite. And it turns out that these are the only cases, and except for genus bigger than or equal to 3, there is some exception. And this is the main result. So the next result is an analog of Hoste and Shanahan for linked quandles. So the result is as follows. So take the genus 1 surface, take the n-quandle. When it is finite if and only if n is 2, 3, 4, 5. And this is a direct consequence of Hoste and Shanahan, because I observed a result of Nebryzovsky and Petritsky that the Dehn quandle of the torus, here 1 is the genus. Torus is precisely the Dehn quandle of the trefoil knot, and for which Hoste and Shanahan had already proved. And for genus 2, D2NS, n is finite if and only if n is 2 and 3. And for higher genus, this is finite for n is 2, for n equal to 2, all genus it is finite, that we already showed. It is the homological quandle. And it is infinite for n other than these values. So there are some values, these values are left over, and we don't know how to answer this question. And our idea of proof use some result from mapping class groups, where people study finiteness of mapping class group by normal closure of Dehn twists. And this is the result of Louis Funar and Stephen Humphreys, which we use to conclude this result. So there are some cases left over which we are not able to address. And of course, residual finiteness of n-quandles where they are infinite still remains. So we don't know whether they are residually finite. By the way, Dehn quandle are residually finite because mapping class groups are residually finite. But if we take their n-quandles, we have no clue how to proceed with that. So I think I will stop here. Thank you very much.